The universe is governed by fundamental forces that control how everything in it behaves. Among these forces, the strong and weak nuclear force are especially important because they affect the tiny particles that make up atoms, the basic building blocks of matter. The strong nuclear force, often called the strong force, is one of the most powerful forces in nature. It is responsible for holding the nucleus of the atom together. An atom's nucleus is made up of protons and neutrons, which are tightly packed at the center. Protons all have a positive charge, and normally, like charges repel each other. So, without the strong force, the protons in the nucleus would push each other apart. The strong force is what keeps them bound together, overcoming this repulsion. This force works over a small distance, about the size of an atomic nucleus, which is incredibly tiny, about 1/100,000th of a meter. The strong force is carried by particles called gluons, which act like glue to hold quarks together. Quarks are even smaller particles that make up protons and neutrons. The strong force is extremely powerful, much stronger than the electromagnetic force, which causes protons to repel each other, and vastly stronger than gravity. However, because it only works over such a small distance, it is only effective within this tiny space of the atomic nucleus. This is why atoms, and therefore all matter, are so small and dense. The energy that comes from the strong force holding a nucleus together is known as the binding energy. This energy is what makes the atomic nuclei stable. The binding energy varies among different elements, making some nuclei more stable than others. For example, the nucleus of iron is very stable because of its high binding energy. This principle is important in nuclear fusion, the process that powers stars, including our sun, by combining lighter elements like hydrogen to form heavier ones and releasing energy in the process. The weak nuclear force. The weak nuclear force, or weak interaction, is another key force, but it operates differently from the strong force. It is responsible for certain types of radioactive decay, like beta decay, where a neutron in an atom's nucleus turns into a proton, releasing an electron and another tiny particle called a neutrino. Unlike the strong force, the weak force can change one type of particle into another. For example, in beta decay, it changes a neutron into a proton. This process is vital for the energy production in stars, where it helps to convert hydrogen into helium, releasing the energy that makes stars shine. The weak force is carried by particles known as W and Z bosons. These particles are much heavier than protons and neutrons, which is why the weak force is only effective over very short distances, even shorter than the distance over which the strong force acts. One interesting property of the weak force is that it can break certain symmetries in nature. For example, it behaves differently if you look at it in a mirror, and a discovery that was surprising to scientists and helps them to understand more about the universe's fundamental laws. Although the strong and weak forces are different, they work together to make atoms stable and allow them to change over time. The strong force holds the nucleus together, while the weak force allows the transformation of particles within the nucleus. These transformations are essential for the processes that power stars and create new elements which are crucial for the existence of life as we know it. For instance, in the sun, the weak force helps to convert hydrogen into helium, which releases the energy that makes the sun shine. Without the weak force, this process would not happen, and the sun would not be able to produce the energy that supports life on Earth. Scientists believe that in the early universe, just after the Big Bang, the strong and weak forces were once unified, meaning they were part of the same force. As the universe cooled, these forces separated into the distinct forces we observe today. Understanding how these forces once unified is a big goal in physics, as it could help explain how the universe began and how it evolved into its current state. Experiments in high-energy physics, such as those conducted at the Large Hadron Collider, LHC for short, aim to explore these forces further by recreating conditions similar to those just after the Big Bang. These experiments could help scientists learn more about the strong and weak forces and how they shape the universe. To conclude, the strong and weak nuclear forces are essential to the structure and behavior of the universe. The strong force binds the protons and neutrons together in the nucleus of the atom, while the weak force allows for the transformation of particles within the nucleus. Despite their differences, both forces are crucial in the process that create and sustain the universe, from the stability of atoms to the energy that produces in stars. These forces are not just important for understanding how the universe works, they also play a vital role in the existence of everything around us, including life itself. As scientists continue to study these forces, we gain a deeper understanding of the universe and our place within it.